Hey everyone, and welcome. Today we're going to talk about something in your home that is critically important but also, well, dangerously misunderstood. I'm talking about your circuit breaker. We're going to get to the bottom of how they really work and bust a myth that could seriously put your home at risk. Let's jump in.
I want you to really let this sink in. This is not an exaggeration, okay? It is a fundamental truth of electrical safety. The idea that a bigger, more powerful breaker gives you more protection is not just wrong, it's a recipe for disaster.
So let's start by breaking down this exact idea, this very dangerous misconception of why bigger is absolutely not better when it comes to circuit breakers.
This really is the central question, isn't it? It feels kind of backward. If a breaker is a safety device, why would a stronger one be more dangerous? Well, the reason is surprisingly simple once you understand what that little switch is actually designed to protect.
To make this super easy to understand, we're going to use a simple analogy. Let's just think of electricity as if it were water.
That's right. For just a minute, forget about volts and ohms and all that technical stuff. I just want you to picture pipes, water flow, and safety valves. This little mental model is going to make everything click into place perfectly.
First up, we've got amperage, or amps. In our water analogy, this is simply the amount of water flowing through a pipe at any given moment. So more amps just means more water is trying to get through.
And look how perfectly this lines up. The wire in your wall, that's our water pipe. The electrical current, the amps, that's the water flow. And the circuit breaker, that's the most important part, that's our safety valve, designed to shut everything down if the flow gets dangerously high.
And this right here is the crucial point. You wouldn't try to force a fire hose worth of water through a tiny little garden hose, would you? Of course not. The pipe would burst. A wire is exactly the same. Its thickness, or what we call its gauge, determines how much electrical current it can safely carry.
So now let's look at what happens when things go wrong. Let's walk through the failure scenario. What happens when a wire that's too small starts to overheat?
Okay, back to our analogy. Imagine you have that small garden hose, but you install a massive safety valve that was designed for a giant industrial pipe. What do you think happens when you crank up the pressure?
This shows you exactly how the disaster unfolds. First, you get high demand. Maybe you plug in a space heater and a vacuum cleaner on the same circuit. They start drawing way more current, more flow than the wire can handle. So what happens? The wire heats up. I mean, it gets extremely hot, basically turning into a toaster element, but inside your wall. From there, the plastic insulation just melts away, exposing the live conductor. And that's when you have a huge problem. That red-hot wire can easily ignite the wood or insulation right next to it. And all the while, your oversized breaker, it's doing nothing because the current is still below its trip rating, even though it's way, way beyond what the wire can safely handle.
Just let that sink in. The wire itself, the thing hidden in your walls that's supposed to last for decades, is forced to act as the safety device. And its way of blowing is to melt down and catch fire. This is the absolute last thing you want.
So this brings us to the breaker's real job. It's time to understand what it's truly designed to protect.
This is it. If you only remember one thing today, please let it be this. The breaker is not there to protect your TV or your microwave. Those devices have their own little internal fuses for that. The circuit breaker's one and only job is to protect the permanent wiring inside your walls from overheating and causing a fire. That's it.
Okay, so now that we've seen the danger and we understand the breaker's true purpose, the solution becomes incredibly simple. It's totally logical. It's really as simple as that. The safety valve must be correctly sized for the pipe it's protecting. The breaker's amperage rating must be low enough so that it trips long before the wire it's connected to ever gets hot enough to become a danger.
And this right here shows the most common pairings you'll find in a home. A 15-amp breaker protects a 14-gauge wire. That's typical for your lighting circuits and standard bedroom outlets. A 20-amp breaker needs a thicker 12-gauge wire, which you'll find in kitchens and garages where you might plug in more powerful stuff. And then you have a big 30-amp breaker, which requires a very thick 10-gauge wire for power-hungry appliances like a dryer. The numbers must always match up like this. So I'll just leave you with this one question to think about. In your home, is the wiring the system, or is it a hidden fuse just waiting to burn? The answer all comes down to that small number printed right on the breaker switch.
I really hope this explainer has clarified this crucial safety concept for you. If you found this helpful, please hit that like button and subscribe for more explainers that break down the complex topics that matter. Stay safe out there.